Hey everyone, welcome back. My name is Elliot, and in this video, we're going to be learning about RL from scratch, or reinforcement learning from scratch. I assume you've already heard of the term RL, hence why you clicked on this video. But my logic for creating this is the limited content on the internet that really explains the topic from scratch in a shorter time frame. If you search up on YouTube RL from scratch or intro to RL, you'll probably see a bunch of results that are 40 minutes, 2 hours long, or somewhere in between. They're fairly long, in-depth videos. I'll be uploading another video soon where we comprehensively build up the code base from nothing. So all the code you're going to see in here, we're going to build that up from absolutely nothing. And it may already be up by the time you're watching this. This video is particularly designed for intermediate and beginner level programmers. If you're an expert, you're going to find this video a bit slow. If you're a beginner, you might find this video a bit fast. I'll try to balance the two. We'll be using Python. Let's get started. So I'm going to try to zip through this next part really fast. Before getting into the fun stuff, I'm just going to give you a description about each file purpose. So it should take a very short amount of time. But we have one called real-time graph. I'm going to show you here. So it just does that. And this is useful because it'll give you the agent rewards over time in real time. So this will allow you to sort of have a better intuition and understand visually what the agent is doing. Yeah, this is sort of just a little tool in your tool belt to help you do that. And of course, you can set up this whole environment using these commands. The next one is demo. So I'm actually going to change demo to, sure, we'll make it for demo. Just going to start up this Pygame file, and I can pretty much use arrow keys just to move this character around. And then when it gets to the green one, which is the goal, it resets the game. So in this one, I can't go through the walls, but in the actual RL environment, you will be able to. This is just sort of, I don't know, this is something I scrapped together really quickly, just for you to understand what's going on. But this is like pretty much the RL environment we're going to be using. So if I just close that. Then the next one is just pretty much the main content of this video. So we have a main, and these pretty much just do the same thing. One is executable, one is a notebook you can play around with. The next step here is just the types of machine learning that you're working with. So I'm obviously not going to go over these now because it would just take extra time, but we're going to be sticking with reinforcement learning. This is the purpose of this video. You can look at this repo to understand, vaguely or generally what each of these mean, but we're just going to be sticking to RL. And so what are like the pros and cons of RL, since that's what we're covering here? Well, some pros: doesn't really require massive or a small data set or data set at all, because you're just using an environment that the agent is interacting with, or the player. These terms are used interchangeably, agent and player. But yeah, it just interacts with an environment and learns about the environment without any like data that it's being fed or anything, just the environment data itself. It can teach humans how to play games. So like, for example, AlphaGo, it might find, little strategies that humans maybe have overseen, or, maybe are too dumb to understand. So it can teach us things about games and, slightly simpler environments that have, very complex strategies. And it can also optimize other complex systems too. And some cons: it can be slow to train. So batch processing doesn't always work. There's ways to get around this, but I'll let you investigate that in your own time. It can be hard to tune hyperparameters. So if you see in this main Jupyter file, we have a ton of these. Those things are called hyperparameters. These little variables that are used to essentially run the game and do the training run for it. You have to tune these so that the agent performs the best way. And so there's a lot of combinations you could have these hyperparameters in. So you can use little tools like autotuners, or automated hyperparameter tuning. So that's a little obstacle you have to navigate through. It can also be hard to debug. So you'd want to use visualization tools like I showed you with the real-time graph Python file. And also the action space is large. So it can be hard to explore all possible actions. Even if we use an example like Minecraft, the number of actions to pick from is huge at each frame. So every single time step or every single frame is what we're referring to here. If you wanted to just break a block of wood, and that's your very first reward, is like, that's pretty easy for humans to do, is break a block of wood. Go, yeah, sure, of course. Wood is like easy, 10 seconds done. But for a reinforcement learning model or agent to do this, it is very hard. You have to hold down the left mouse button out of all the possible actions for like 300 frames. That's pretty hard to do, statistically speaking. So you can use other techniques like pre-training from scratch and like mimicking human gameplay, behavioral cloning. But this is not what I'm going to cover in the video. This is just, a way to get around these. But for this example, for this video, I'm going to be using a very simple environment. So the action space it's literally only going to be 4, up, down, left, right. And then so our environment is going to be, like I showed you before, that little demo.py file with the grid game. That's going to be our environment. So the agent can move up, down, left, right. It's in a 5x5 grid or a 4x4, whatever you choose. The agent and the grid, the agent and goal are initialized at random positions. So they're not going to be at the same one, but they're just going to be like random each time so that it doesn't, just use the same pattern over and over again. It's going to be penalized each time step. So this is going to help the agent minimize the number of actions that it takes to reach the goal, because it's being penalized for every decision that it makes, regardless of if it was good or bad. And then I include a slightly more complex reward system for its decisions. So it's rewarded as a function of delta distance from the goal. So this pretty much means if you go, the closer the agent moves to the goal, higher the reward. And if it moves further from the goal, lower the reward, or it gets a negative reward. This is a very simple environment to understand the mechanics of reinforcement learning. We'll use this environment to understand mechanics of RL and how to build a Q-learning agent. So now you might be asking, what is this Q term here? So we have deep Q-learning and normal Q-learning. So Q-learning is pretty much a table to store the Q values. This is useful in smaller action spaces. Q value, in the Q-learning table, this is actually like calculated. You can actually use algorithms to figure out what this value is. And so it's a little bit easier in that regard. But we're going to be sticking with deep Q-learning in this video, mainly because it uses neural networks. Neural networks are cool, and it uses the same concept of Q-learning, but applies it in an optimization sense. So we're actually using a neural network to optimize. And so pretty much, like without even explaining, I'm going to jump past all of this content and just break down to you what exactly these neural nets are doing. And if neural networks strike your interest, I actually have a video on this. You just click on this, it'll be in the video description and the GitHub repo. Pretty much, you're just trying to use this neural network. It's called a deep Q network, or a DQN in short, to predict what the rewards are going to be. So you have some actual rewards that you get from making decisions, and then you have the expected rewards. And so the point is to minimize the difference between these actual rewards and these predicted ones, so that you can have a neural network to best approximate what is like the best thing to do in any given state, right? That is the whole point of the neural network. And so before I actually go to conclusion here, I'm actually going to give you a little demo on the code itself. Actually, before I begin the demo, I should probably add this little cool feature called epsilon decay. So is another new term, there's a lot of new terms here, but epsilon decay, in short, is a way to balance exploration and exploitation. So this epsilon is a hyperparameter, pretty much is between 0 and 1. If it's 1 or close to 1, it's going to prioritize exploration. So it's going to pick more random actions and try to find something unique. Whereas if it is closer to 0, it's going to use what it already knows to continue exploiting the game. So you'd want it to start off with being super random, so it would figure out, little cool tricks here and there that it can perform and learn a little more. And then once it has learned those from being random and making a ton of mistakes, then it can continue to exploit those and just make little increments, like every once in a while, to improve it just a little bit. Even though it already knows a lot about the game, it can still make little incremental changes. So the point of epsilon decay is to start it off with a lot of exploration, a lot of random actions, and then get it to a point where it now uses the knowledge that it has learned from all the mistakes and benefits from those random actions to exploit the game. And so without any further ado, let's actually go into some code here. So I'm just going to go into this Jupyter file. So in this Jupyter file, I have a bunch of libraries. We use PyTorch, we use random for generating random actions, we use time to estimate time, and then math for some scaling, and then just Pygame for the actual instance itself. So we're going to use CPU for this. You don't really need GPU because this is hard to batch process. This we would need to, introduce more complexity into the script, which I just don't feel is necessary to teach you the concept. But we have a bunch of hyperparameters here, which I'll go over first, and you'll see how these make sense more later. But pretty much we have num episodes. So this is how many instances of the game is it going to play. This is how many times it's going to reach the goal. It's going to reach a goal 10,000 times, reset 10,000 times. And then this D state here is just the state dimension. So dimension, state dimension. It's going to be 5. So 5 by 5 is a 25 tile game. Action size is 4, like we discussed earlier. The discount rate is pretty much how much it's going to favor current rewards over future rewards. So if it's favoring current rewards, it's going to be closer to 0. That means it's like decaying more. So if we have like 0.8, after the first one, it's going to be 0.8 importance, and then 0.8 times 0.8. The second one is going to be 0.64 times importance, if that makes sense. So it's going to decay over time. And so the higher this number is, the slower or the more, I guess a simpler way of putting this is the more it will prioritize future rewards. So that's that hyperparameter. And then learning rate is just pretty much how it will adapt through each time step. How much can the actual parameters themselves adjust? So that is learning rate. How much can it advance? Pretty much what it says, learning rate. How fast can it learn? How quickly, how much optimization is made each time step. And then this whole epsilon start or EPS start, EPS end, epsilon decay. This is where it starts at. It starts at 1. A lot of random stuff going on. Then it ends. It's exploiting. And this is just a decay rate that you can play around with, just to change how quickly it decays or how slowly it decays. Time step reward is -1. This is just the reward it gets every time it makes a decision or evolves one time step. And then dropout is a concept in neural networks, but I'm not going to cover that right now. It's pretty much just helps the training run and the actual inference run perform a certain way. So training run will be a little bit more randomized and have some noise, and then inference will be the same without that noise, so it performs better than training. And then our scaling is just the reward scaling we have in place. So I have a little epsilon decay function that we use to decay the epsilon over time. This is self-explanatory. This should not be hard to understand. Then we have our neural network class here. So it's pretty much just a feed forward. So linear value activation, and then the linear. I cover this in a lot of depth in my neural network video, which you should take a look at if you haven't already. And then just chiming init, which I did not cover, but this pretty much just initializes the weights a certain way so that it is more likely to not break. But yeah, so if we scroll down even further, we have a grid game class. So we have a state size, action size, a model that we use this is the DQN model or DeepQ network. A reset, so this will reset the game instance to new player and goal positions. The optimizer is what optimizes the neural network. The criterion or the loss is the loss that we then plug into the optimizer to make the neural net better at doing its job. And then we have a bunch of methods in here. These I don't think are going to be super hard to understand. You could just sort of go through these step by step, even plug it into something like GPT or Copilot or GPT-4 and say, hey, what is this doing? So we have a get state as well, a calculate distance. So this is going to, like we discussed in the README file, it is, where was it? Yeah, closer agent moves to the goal, higher the reward, further from the goal, lower the reward. So that's pretty much what it's doing. This calculate distance is going to feed into our step. So If this delta distance is greater than 0, if previous is greater than new distance, that means we're going to give it some reward. And if it's less than 0, it's going to give it negative reward. And we scale this by dstate pretty much. So this is just a little reward thing I have in place here. And we give it time step reward, and if it reaches the goal, we give it 100 reward. So we have 4 different types of rewards: time step, positive reward from delta distance, negative reward from delta distance, and then reward for reaching the goal or finishing the game. And then a train step in here. So this is actually where a lot of the magic happens. We have an action, a reward, and then done. So don't worry too much about those right now. But the main part that we're concerned about is this massive mouthful right here. So I'm going to zoom in a little more. So you pretty much have this, these next state values times the discount rate. So like we were going over before, discount rate is how much it's going to prioritize current rewards versus future rewards. And then we multiply this by 1 minus done. But like, don't worry about this too much right now. This is a little separate. What we really care about is our reward structure. This stuff right here is going to be trivial once you are able to really document and understand the Bellman equation, which is how Q-learning works. That's something you can look into on your own time. But what we really care about is this whole reward thing. So what I do is I use torch.tanh, which will pretty much make the value it'll normalize it between -1 and 1 using a tanh activation function. And so what we do is we just take the reward, the total reward that we have gotten. So reward is pretty much just what we got from this step here. It returns this reward, and we use that in here. This reward, we pretty much just take the reward, we normalize it, and then we multiply that value by some R scaling. So the reward can be like max. If our R scaling is like 2, for example, like it is up here, that means the reward can be between -2 and 2, just because of how we scale that. And then so you have your loss, of course. This is what gets your loss or your accuracy for that neural net prediction. And then we do just some steps to help optimize the network here. This is in my neural networks video, but I'm not going to go over this train step as much, like in depth, mainly because it's something you could plug into GPT and understand more. But yeah, so then we have a select action, which is just it's just going to select an action for us based on that epsilon value. So epsilon is like how likely is it to be random and how likely is it to just follow what the neural network is doing already. This is relatively simple. I'm not going to explain this. And then we initialize our policy network or our deep Q network. It's just like a learning, essentially, policy that it learns about the environment. And then the game instance itself with the policy net as the model. And then we just do a training run. So I also cover training runs in my neural networks video. But yeah, so pretty much everything is just done sequentially. This is how it will improve. And it will print out the performance over time, of course. And then this, where did it go? I'm going to actually remove this bit of code. This should not be here. And then this last block here just does the inference. So after the training is done, it will use the stuff that it's learned to actually play a game for us. So if I go ahead and say run this for 3,000 epochs and then come back, you guys will see how epic this game is. So I'll go ahead and run this. Okay, so I actually needed to play around with some hyperparameters. I didn't change num episodes. What I did is I changed discount rate from 0.98 to 0.9, and that helped. I changed learning rate from 5 times 10 to the -4 to 1 times 10 to the negative 3. So 10 to the negative 3. And then I changed epsilon decay to lower. And then I changed dropout as well. I lowered it by 0.1, and that maybe helped. I'm not sure. But probably what happened was the learning rate and discount rate had the biggest effect on this. So, just playing around a little bit can increase your optimization process. And if we actually look at the raw performance here, go all the way to the top, starting off like 97, it drops to 45. This is just like random actions, right? So it happened to pick a good one here, happened to pick a good one there. And over time you see it's like, high 90s, goes to 68 there. And then after a while, it doesn't really go below 85. So there's like 85 there, 87, 98, 89, 99, 99. There's a 78, which is interesting. And then it takes about 36 seconds to train for 10,000 games, which is a lot. And so if I just like show you what this looks like, if I just run this here, like it's gotten pretty good. And it might look a little jittery. That's just because of how Pygame is loading. But yeah, it'll thrash every once in a while. So this is not what we want. But I can just speed this up, change time.sleep to 0, and just run it, and it'll be like super fast. And it finishes 100 runs just like that, like all done. Average moves is 11.89, which is pretty good. Of course, there's like weird ones where it'll thrash for a bunch of moves, so like negative 200. But that's a problem on its own that we're not going to deal with this video. But yeah, that's that. I'll just run this one more time for the outro. So to end this off, for those wondering, yes, I do one-on-one tutoring and consulting. So if you're interested in that, feel free to shoot me a DM on Fiverr, Twitter, LinkedIn, or Discord. All these links will be in the YouTube description and the GitHub repo. If you found this video helpful, you should definitely subscribe. It not only supports me, and it honestly doesn't matter if it supports me. What really matters is that this content gets out to other people so that they can learn and the world can become a better place just by more people being informed about the technology and more people knowing how to build it. And so therefore we get more people building and that sort of thing, and you go down that trajectory. But anyways, if you want to see more content like this, please let me know. Just shoot me a DM or whatever in Discord or whatever. I'm always looking for new ideas. But yeah, that's all. Thanks for watching. I'll see you in the next one.